is running into class, but that's fine because we're just answering questions right now, which I was going to start out class doing anyway. Recording is working on starting. Right now we were doing number 25 from the 5354 homework. We are not having a quiz today. No, I sent an email about it. Everybody, the majority voted to not take a quiz today. So we're not having a quiz. Isabella, I'm thinking about your question, and it's bringing me back to our notes from last week. Let's see. Some properties, I think. Setting active notes and properties. All right, well, that's odd because one of my sheets got lost. The exact sheet I wanted to reference that has to do with your question, Isabella, or your book to find the MVT. My notes go straight to average value. What happened? Clearly something got lost. All right, that's fine. Open up your book. But no, in general, when you're looking for the value of U that satisfies the mean value theorem, you're looking for wherever you have the average value set equal to the function value. That's so bizarre. This might even be it. I don't know. Or this might be the notes I used to teach you from. It is. It somehow got stuck in with my actual instructional notes. There it is. Okay. That stays here. Okay, so I'm going back to Isabella's question about this f of u times b minus a business. So the deal with the using the b minus a, the way that you're talking about it, Isabella, is that would be the value of the definite integral. So because we used, I just had it. There are way too many pieces of white paper with calculus on them. Okay. We use the average value when we computed our integral. So we were given this integral, and we already used the 1 over b minus a portion here. If we hadn't used that yet, then we would need to use it at some point to find, we would have, I want to write this. I'll bring it back in here. A to b f of x dx 1 over b minus a times f of u. So f of u being the average value is what we divided by over here. So if we wanted to, we could have found the value for the integral of f of x dx, which in our case would have been 27, but then we would need to still solve for u. So to do that, we would have needed to multiply 27 by b minus a, which is 3, divided by 3. B minus a. Did I write this backwards? Going back here. Yeah, sorry, I wrote it backwards here. Sorry, I'm not used to looking at it in the definition form. I'm used to looking at it in this form. So yes, technically this is part of your definition. You could have found the integral of f of x from 0 to 3, and you would have just neglected this 1/3 piece, and you would have gotten 27. And then to solve for u, you would have needed to isolate f of u. And you would have done that by then dividing by b minus a on both sides, which means dividing by 3. So f of u in this case, regardless, and if you want, we can replace all these c's with u's if they're bothering you. They're bothering you. No matter what you do, you're going to have to end up dividing by b minus a. So that was the way it was presented in the definition for the mean value theorem. But we normally would just use it as 1 over b minus a times the definite integral. Does that make sense, Isabella? Okay, cool. Sorry, that was like a whole fiasco getting to that explanation. Okay, I'm going to put these off to the side so I can scan them for your office hour notes. If you have more questions to go over, though, I know that Morgan had one. Might as well add that to the notes. Now I don't know where this paper goes. Ay, ay, ay. Just forget it. All right, let's see. Morgan wanted to do number 21. Let me find it. Morgan, is this number 21 like in, did I assign that? 5, number 21? Because I don't see it, I only see it goes up to 18. Oh, 5-3. Okay. That's okay. Okay. 3, number 21. Okay. So this is the integral from 1 to 2 of x squared minus 12 divided by x to the 4th dx. Okay, so for this one, anytime your denominator is in the form of a monomial, so a one-term polynomial, you can just split this up into 2 separate fractions. So this will be x squared over x to the 4th minus 12 over x to the 4th dx. And then you can rewrite it as x to the negative 2nd minus 12x to the negative 4th dx. And then you can integrate. So x to the negative 1st divided by negative 1 minus 12, x to the negative 3rd divided by negative 3 And then that's going from 1 to 2. And before you evaluate it, you'll probably want to simplify it because evaluating it like this, it's probably not the best idea. So you'll have negative 1 over x, and then plus, because you have minus a negative 4 divided by x cubed, and you'll take that from 1 to 2. So that leaves you with negative a half plus 4/8 minus negative 1 plus 4 divided by 1. So this is negative a half plus 1 minus 4, which gets you to negative 3. Okay. In the office hour, just so that you are aware, because I'll put the notes up, I did number 25 from 5-4, which was a piecewise function. That was the one I was doing as class started. And then we did some properties questions from 5-4, number 15, and from 5, was it 5-3? Well, it should be 5-4. Number 14. And then from 5-5, we did number 8, which I had gotten a couple of email questions about. We did 5-5, number 2. This was another one I got a couple different questions about. And then we did 5-4, number 26 with the average value. I did get a couple questions on this one or one like it via email. Were there any other questions you guys had from the homework? Okay. So my job tonight is to finish section 5-5, which is probably going to take the whole time. But if it doesn't, when I'm done, you can go. We'll see how long it takes. Okay, so today I want to talk about 5-5 and how it relates to definite integrals, and then I want to talk about a few different types of integrals you're going to see that are not definite integrals, but just special types of integrals I want to make sure that you're aware of. And this is substitution, and today we're going to do it with definite integrals. Okay, I'm going to give you a change of variables formula. Now, some students really like this and they use it all the time. Other students are very stubborn, like I was when I was in calculus, and they're going to always back substitute. Now, I can't make you do one way or another, and honestly, it doesn't really matter to me if you use this method or if you back substitute. I just want to make sure you don't try to use both. So I'm going to show you this method, and there have been years in the past where I've just only done back substitution because it's what students tend to do. However, your calc teacher, your calc 2 teacher, is most likely going to be using this method for changing your variables. And I don't want you to be really confused, being like, what the heck is my teacher doing? I have no idea. I've never seen this before. And then they're going to say, who was your Calc 1 teacher and how come you don't know this? And then it makes me look bad. So it is very important that you at least see it. Whether or not you use this or back substitution's up to you. This is a change of variables formula for definite integrals. Oh, I also wanted to mention that because tomorrow is an optional review session, and I will record it because I know technically we don't have class Tuesdays, so it's definitely optional. I will answer whatever questions you have from either the final exam review sheet, by which there's a key up there, by the way. I posted a note on there saying that starting with, I think, number 40, the numbers are all off by 4. Sorry, but you should be able to match it up just fine. Or you can ask me questions on 5.5 if you want, but it's your time. So it'll be from 6 to 8:10, just like we normally would have class. And also, I won't be having an office hour because the whole time will be just for you to ask questions. So instead of coming on at 5:30, I'll just be on at 6, and that will be all your time. I will not be teaching anything tomorrow. There certainly will be nothing new. I don't have anything formal planned. It's really just going to be me answering any questions you have. Let's say you haven't gotten a chance to get to the final review sheet yet. That's fine. If you want, you can stay logged on to Google Meet and sit there at your house and work on your review sheet with your camera off. And if you have a question, you can pop on and ask me your question. I will be sitting here until 8:10, regardless of how many people are currently asking me questions. So it's not like all of a sudden people stopped asking me questions and I'm going to stop and go offline. Yes, you will have another homework to do after tonight for 5.5. So there will be, you might have questions on that too. But I will be on till 8:10, regardless of whether or not I'm sitting here silent from 7 to 8:10, even though I really doubt that's going to happen. I know you guys too well for that, which is a good thing. You are good at asking questions. But that's your time. Please make use of it if you feel that you need that. If you don't, that's also fine. It's optional. Just wanted to remind you, but I will be on at 6 tomorrow. So if you're one of those people who usually comes on at 5:30, don't come on at 5:30 tomorrow unless you just want to mingle with your other 5:30ers. How many questions will be on the last homework assignment? I don't know. I haven't put it up yet. Hopefully it shouldn't be too long just because it's technically due Thursday regardless, but I want you to have it done by Wednesday because your test on chapter 5 is Wednesday. So that'll give you 2 solid days. Technically 1 day in like 22 hours to finish it. Okay, sorry, I forgot to do that before I started introducing this. So, all right, so let's say you're looking at a definite integral from a to b where you have some function, some composite function f of u of x. And inside your integral, you have a u prime of x dx. So this is a situation where you would use integration by substitution. What you're going to do in that case is when you change your integral into a u integral, it's going to be of something like f of u du. You can no longer use your x limits because remember that this means x equals a and this means x equals b. That's when you're looking at a dx integral and you're taking your limits from a to b, you're talking about where x is going. And if you think about what that means in terms of area, that should make sense to us. We're talking about some function in x. We're looking at the area from some finite value a to another finite value b. When we're looking at u, we need to change our upper and lower limits of integration to correspond to our new function f of u. So that means what we need to have now are new upper and lower limits, u of a and u of b. So I'm going to show you how to change out your limits of integration so that we can substitute with definite integrals. I am going to show you also in maybe like one example how to do this with back substitution. Like I said, some of you are going to back substitute regardless. What I'm worried about is I've had some students who learn how to do this, they do it right, and then they still back substitute, and then they evaluated the wrong variable. What I mean by that is they switch their upper and lower limits to U limits, but then they back substitute and turn their integral back into X and evaluate the X at the U limits. And it's like overdoing it, and then everything is still not right. The nice thing about this is you don't have to back substitute. So normally we do an integration by substitution problem. You get to the end, you have some function in U, and then you swap back in for X. If you use this formula and switch your limits to U limits, you don't have to back substitute for X. But either back substitute or do this. Don't do both. So let me show you how this works with example. I want to say we're on example 16. Let's see if that sounds right. Yeah, that looks right to me. Example 16. This is the integral from 0 to 5 of x times the square root of 25 minus x squared dx. So this is very similar to an integral that you would have seen in your asynchronous work over the weekend, where you end up having this U substitution problem. The difference is that you have now these upper and lower limits of integration. Now, from what you saw last time, you're going to let U be the value that's underneath the radical, which is 25 minus x squared. Then du will be negative 2x dx. So we're proceeding right now as we normally would. Then you'll have negative 1/2 du is x dx. And this is good. So the x dx is negative 1/2 du. And then this piece right here will be u to the 1/2. Morgan, go ahead. What's your question?
How did you get negative 1/2 du?
Oh, by dividing both sides by negative 2. So I kind of looked and said, well, I don't have a negative 2x dx. I just have x dx. So to create x dx, I just divided both sides by negative 2. And if you divide by negative 2, you're multiplying by negative 1/2. Does that make sense?
Yeah, so can you just do like du divided by negative 2, or do you have to put it under the negative, or put it under the 1?
You can do du divided by negative 2. Yeah, that's fine. I think personally it's easier for students to do the arithmetic on it if it's written as a constant multiple, but it wouldn't be wrong if you divided by negative 2. And if you have gotten used to doing that and you find that that's easier, then do that. Other questions there? Okay, so now I want to substitute everything out in my integral. I'm not going to put the limits back on though right now because these are the x limits. So what I'm going to have is negative 1/2. That's from this du piece here. And then I have u to the 1/2 du. So we have the negative 1/2 du and the x to the 1/2. Everything's accounted for. The only thing I have to do now is switch the limits. Before I work on the upper and lower limits, does anyone have a question about the substitution? Okay. I try to do this just by kind of pulling the pieces out so that you can see how everything matches up. If you want to do this on your test, feel free if you find that that's easier. As a student, that helped me to visualize the substitution. All right, so what you're going to do then is you're going to look at these limits and you're going to sort of use this ideology here. Like you started out with x equals a and x equals b. So it's right here, switch limits to u. So I had x equals 0 and x equals 5. I'm just going to leave them as upper and lower just because I don't want to accidentally switch them. Now I know that u is 25 minus x squared. So what I'm going to do here is I'm going to rewrite these in terms of u just by using this substitution that we already created. So if I know that x is equal to 5, then I know that u is equal to 25 minus 5 squared, which means that u is actually going to be equal to 0. And we'll do the same thing for the lower limit. If we let x be 0 and we know that u is 25 minus x squared, well, then we're going to have u equals 25 minus 0 squared. And we'll get u equals 25. Now, these are my new upper and lower limits. I want you to be careful, though. Remember, I kept these in the right order vertically. So this x equals 0 was the lower limit, and x equals 5 was the upper limit. That's still going to be the case here, but it looks tricky because u equals 0 is actually the upper limit. So when you put these back into your integral, it actually looks like this, where instead of going from the lower number to the higher number, you're doing the opposite. You're going from the greater number to the lesser number. Now, personally, that drives me nuts. I don't like it. So what I do is recall the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx. This was a property that we talked about in 5.4. What this is saying is that I can switch the limits of integration as long as I switch the sign on the integral. So I don't want them written in terms of greater to lesser. So what I'm going to do is I'm going to actually rewrite this. Now, you don't have to. I just think the fewer negative signs you have to deal with, the better. I'm going to make my integral positive. Right now it's negative 1/2. I'm going to make it positive 1/2. And as long as I do that, I can switch the upper and lower limits of integration. And now instead of going from 25 to 0, I'm going from 0 to 25, which I'm a lot more comfortable with. We are going to evaluate this. Before I do that, are there any questions? And by the way, if you would like to, if it helps you, you can write u equals 0 and u equals 25 in your upper and lower limits. And if you do that, it might help you to understand that you're not supposed to back substitute. And in a minute, you'll kind of see why. But we're going to leave the half out front, increase the power by 1, and divide by the new exponent. So our new exponent is 3/2. That means I'm going to multiply by 2/3. I hope we're getting pretty quick with those. Now, this is a u result. I'm going to take that from u equals 0 to u equals 25. So what I was saying at the beginning is that sometimes students switch their limits to u limits, and then they'll go here and they'll say, okay, well, this must be 1/3. Okay, fine, u to the 3/2 from 0 to 25. And then they back substitute and they'll say, well, okay, u is 25 minus x squared. And then they'll plug that back in here and they'll keep these limits on. Don't do that. You have to decide if you're going to do this method or if you're going to back substitute. The nice thing is that you've already done basically the back substituting by switching to u limits. You don't actually have to rewrite this in terms of x because you already are evaluating u from 0 to 25. So now you can say that you have 1/3 times, and remember the 3/2 power? is taking the 1 plus 1/2 power. I'm going to write it as 3/2, and I'm going to remind you of how to simplify that, but it will, I think, help you to simplify. And then we'll take off the lower limit of 0. So 25 to the 3/2 is 25 to the 1st plus 1/2. And again, I'm showing more work than I would expect to see from you here, just because I want to make sure everyone kind of sees where this comes from, just to evaluate things a little bit more quickly. So 25 times 5 is 125, and then your denominator will be 3 since you're multiplying by 1/3. Get used to this number. For some reason, in Calc 2, 125 thirds comes up all the time. I just don't know why. Just this once, I want to show you what this would look like if you decided to back substitute and not switch your limits. Before I do that, are there any questions here?
I don't understand like the purpose of it.
Oh, the purpose of it is just so that you don't have to back substitute. It's just cleaner. You'd be surprised. Most of the Calc 2 teachers that I've ever seen don't back substitute in a definite integral. They always switch their upper and lower limits. When I was in college, my teachers always did this. They did not back substitute, ever. I don't know. It's just more, it's just cleaner, I guess.
Weird something.
Yeah.
Okay, thank you.
Is that a good enough explanation?
Yeah, I was just confused because it kind of seemed like we were doing exact same thing, but just like changing the limits.
Yeah. I mean, it's basically the same exact thing, just in a different order. Because no matter what you do, you're going to evaluate this, which I'll show you in a second. Go ahead, Victoria. What's your question?
So we don't need to add the plus c to the equation since you're just solving for u.
Right. Remember, with definite integrals, we never add the plus c. We always just evaluate using the FTC. We don't ever use the plus c.
Okay, cool. Thank you.
Other questions on this result? Burfin's question totally reminded me. I was doing this bar class yesterday, and the instructor was like, you know, you got to do upper body just because. She's like, I don't know, just because. And I just burst out laughing because I was like, she doesn't know. And I feel like I tell that to my students all the time. They're just like, why do we need to do this? And I'm like, I don't know. It's good for you. Now I'm just like, just because. But yeah, I feel you. Okay, so my note to you here is, if you don't switch your x limits to u limits, then back substitute for x. And use the FTC. Okay, so what that would look like in this instance is, we started off here with this u substitution. U equals 25 minus x squared. We rewrote the integral in terms of u. We would have then -1/2 times the integral of u to the 1/2 du. But if you don't switch to U limits, then don't put any limits on this right now, because if you put your original limits 0 to 5 on here, technically that would look like they were U limits when they're not. You could say x equals 0 to x equals 5 if you wanted to keep them on here as a definite integral, just so that you have them. Just make sure you understand that they corresponded to x. And now you can integrate this the way you normally would. You would still have a negative on it in this case, because we're not going to switch the limits. Technically you could, but I probably wouldn't in this case. So you take -1/2, and then you're still going 2/3 u to the 3/2, and then you're going x equals 0 to x equals 5. Don't forget your x's. You don't want to send that from 0 to 5 on u. And then this would leave you with -1/3, and then 5 to the 3/2 minus 0. Oh, wait, I'm missing a negative. Oh, I didn't back substitute, that's why. See, it's like I can't even try to back substitute, even when I want to. -1/3 u to the 3/2. Sorry, getting ahead of myself. X equals 0 to x equals 5. And then you would replace u with the expression that it is equivalent to written in terms of x, which we said was 25 minus x squared. So pop that back in. To the 3/2. And that will go now from 0 to 5. Now, once you have these matching, if you want to drop the x equals, that's fine, because you know that the variables are matching. You don't need to worry about it in that case. So you'd have -1/3, and then 25 minus, and then 5 squared is 25 to the 3/2 minus, and then 25 minus 0 to the 3/2. And this would be -1/3 times 0 minus 25 to the 3/2. And we just said that 25 to the 3/2 was 125. Minus a negative is positive. You would still end up with 125/3. Okay, so I'm not going to keep showing this. I'm going to stick with one method. However, even though I don't ever show this very often at all, like half my students will keep doing this. I basically show it to you just so that you know it's an option that's available to you. And I also want you to understand the difference between these two. We don't back substitute for x with the method of changing variables. If you are going to back substitute, don't change your variables. Leave everything in terms of x. And it's always a good habit to write your variable in your limits of integration, especially if you switch off from one method to the next. You might find that depending on the integral, if it's a really basic, straightforward integral, it might be easier to back substitute than change your limits. So it kind of depends for me. It is true that sometimes I do back substitute, but on something that's slightly more complicated like this, I wouldn't do it. So you'll probably find that before the day is over, I end up back substituting on something instead of switching my limits. You just kind of do whatever the problem seems to fit best. Okay, so let's look at another one of these. We'll do example 17. So this is the integral from 0 to 4 of x divided by the square root of 9 plus x squared dx. And this is very similar to the last example. I considered skipping it, but it's pretty short, so we might as well just do it as a little bit of reinforcement. So u is going to be your radicand, 9 plus x squared. And right off the bat, I think sometimes students get confused just knowing, is this a u substitution or isn't it? There's no way that you could rewrite this without having it be a u substitution. And it definitely doesn't fit any of our inverse trig formulas. If we had a square root in the denominator, we would be expecting a minus sign, and we also wouldn't be having a variable in the numerator. So definitely not inverse trig. So a lot of times substitution is going to be the way to go. So that's the way that I'm proceeding here. Du is 2x dx. And I don't have 2x dx. I just have x dx. So I'm going to rewrite this as 1/2 du is x dx. So the x dx is now being represented by 1/2 du, and in the denominator, I have the square root of u. However, the square root of u is in the denominator. So when I rewrite this, I'm going to rewrite it as u to the negative 1/2, just because, well, if you want, we'll just keep it the way it is for now, and then we'll rewrite it in a second. But you have 1/2 and then du divided by the square root of u. And then we'll switch our limits of integration. Right now I have x going from 0 to 4. We'll switch those to u limits. So x went from 0 to 4. I'm going to leave the 4 as the upper just so I don't switch their order. And if x is 4, u, we already said, was 9 plus x squared. So u will be 9 plus 4 squared, which is 9 plus 16, which is 25. And then for the lower limit, 9 plus 0 squared is 9. And again, by switching our limits of integration, we're sort of showing a little bit more mathematical sophistication. Back substituting is a little bit more rudimentary. It's really the best explanation I have for you. So this will be 1/2 times the integral from 9 to 25 of u to the negative 1/2 du. And then we'll integrate. Increase your exponent by 1. That gets you to the positive 1/2. When you divide by positive 1/2, you multiply by 2. And we'll take that from 9 to 25. And the 2's will cancel. And this leaves you with the square root of 25 minus the square root of 9, which is 5 minus 3, which is 2. Remember that you can always check these in your calculator. I showed you how to graph these, and then second calculate number 7 finds the integral for a definite integral. So you can always check something like this in your calculator, especially if it's an integer answer that you can easily just verify by inspection. Okay, questions on 17. Wonderful. Let's do another one. This one will be a little bit different. So this will be the integral from 0 to the square root of e minus 1. Already I can tell people are not liking this, but it's going to be okay. We'll have x cubed divided by x squared plus 1 dx. Now, I actually did several that were like this in the asynchronous work. One thing I don't want you thinking, I mean, you can have the thought and let it go, is inverse tangent. Remember, if this was in the form of an inverse tangent, I would be looking for du divided by u squared plus 1. U squared plus 1 in this case is x squared plus 1. So I'd be looking for dx in the numerator. But I don't just have dx, I have x cubed dx. So there's no way this could be an inverse tangent integral. So we're going to have to set this up using a substitution. Sometimes, if you don't know what your substitution should be, you just let u be equal to the denominator. And if that bothers you, because some of you are thinking, like, wait a second, shouldn't u be 1 degree higher than du? So shouldn't u be the numerator? We're going to have to create the numerator, because if you let u be the numerator and then take its derivative, you will get something in the form of x squared, but that's going to leave you with a du in the denominator, and you can't fabricate this 1 out of nowhere. So my suggestion to you is to write u equals x squared plus 1 and just let u be your denominator. When all else fails, try that. Now du is going to be 2x dx. Okay, fine. At least make it an x dx, because you definitely don't have a 2 anywhere in that numerator. Now, if you're having a hard time seeing where this is going, you can always rewrite your integral as x, because we already have the x dx. And then you can isolate the other portion of this numerator as x squared. And hopefully that will help you to see this a little bit more clearly. I left some space over here because I want to rewrite my limits in a minute. And I guess technically I could put the x limits back on here, because I still have this written in terms of x. Sure, might as well. But we haven't actually changed anything yet. We've just sort of split this up into some factors that it's going to help us to see things a little bit more clearly. So the x dx is now being represented by 1/2 du. And the x squared plus 1, we're letting be u. The only thing we have left to substitute now is x squared. And we can do that by saying that x squared is u minus 1. Just by solving for x squared. Okay, so we'll rewrite this integral now. I'm going to leave some space to switch the limits out. But the 1/2 I'm going to pull out front, just so it's not distracting me. Then I have u minus 1 over u du. Now, of course, I'm going to rewrite this by splitting this up into 2 fractions, because I have a monomial in the denominator. But first, I want to switch my limits of integration before I forget. So let's switch to u limits. So I went from x equals 0 to x equals the square root of e minus 1. Now, if you feel like, holy cow, this is crazy, I'm evaluating this square root of e minus 1, you're going to be doing it regardless at some point or another. whether you do it now or after you back substitute. It's not, one method is not any easier than the other. It's just a matter of personal preference. U is x squared plus 1, so you'll have the square root of e minus 1 squared plus 1. The square root squared just leaves you with e minus 1 plus 1, which is just e. Arrow's bothering me. I want it to be an equal sign. And then as far as 0 is concerned, well, I know that u equals 0 squared plus 1. So u is equal to 1. So I'm going to be going from 1 to e. And those are my u limits. U equals 1, u equals e. Questions on that? All right. Well, now that you have noted this, you know you switched it, you don't have to worry about any back substitution. You can go ahead and just rewrite these as just 1 to e. And then when you rewrite the integral, you're going to write it as u over u minus 1 over u. So that's 1 minus 1 over u du. U over u minus 1 over u. In case that was too subtle. All right, now we'll integrate and we don't have to back substitute because we already wrote our limits in terms of u. We can just use the FTC and we're done. So we'll have u. Oh, and if you don't like the, well, of course you like the 1 over u. We already know that 1 over u is the derivative of the natural log of u. So yes, definitely leave it like that. Minus ln absolute value of u, and you'll take that from 1 to e. Now, it doesn't necessarily have to be the case all the time, but usually if one of your limits of integration involves e, that's sort of tipping you off that somewhere in your integral, when you evaluate it, you're going to have a natural log. Doesn't have to be the case. You could just evaluate some crazy expression using e. But usually if there's an e in there, there's a natural log to go with it. So just something to consider as you work your way through, just getting used to knowing what to expect here. Okay, so we're going to rewrite this as 1/2 times, and then e minus the natural log of e. E is positive, so you can drop the absolute value bars. The 1/2 gets applied to the entire quantity. And then you're going to subtract off, because this is the FTC, you're always subtracting the upper limit minus the lower, 1 minus the natural log of 1. So these minus signs are in here just because your integral had a minus sign in it. This one is because of the FTC. Sometimes students aren't sure where the signs come from. And then you're just going to simplify that. So you'll have 1/2, and then e minus, the natural log of e is 1. Then you'll have minus 1 plus ln 1, which is 0. And this leaves you with 1/2 e, and then plus 1/2 times -2. You can write this in so many different ways. Just leave it as 1/2 e minus 1. Questions there? Terrific. Example 19. I like this one just because it looks confusing to students, but it's not that bad. And anything that looks confusing that we can make seem a little bit less crazy is always a good thing in my book. This is the integral from pi over 3 to pi over 2. Also, it's a trig function, so always a good thing. This is the cotangent squared of x over 2 times the cosecant squared of x over 2 dx. Trying to remember if I did one similar to this on the asynchronous notes, and I think I did. It wasn't using these two functions, but it was the same concept. This time we'll just apply the definite integral here. I want to say on your asynchronous notes, it was something like tangent to the 7th times secant squared something. So what you're doing here, remember, anytime you're using a substitution is you're looking for a derivative somewhere inside the function. So you're kind of thinking in advance, what could you be? Where do I have a derivative? Remember that the derivative of tangent is secant squared. Therefore, the derivative of cotangent is negative cosecant squared. d dx of cotangent x equals negative cosecant squared x. So we're going to use that derivative to come up with our substitution here. So we don't actually have x, we have x over 2. If you prefer to call that 1/2 x, so do I. It'll be displayed as x over 2 most of the time, which is why I left it like this. Want you to get familiar with what you're going to see. So if you want to think about letting u be the cotangent of x over 2, then you can let this guy just be u squared. So we'll formalize that. We'll say that u is the cotangent of x over 2. Just to the first power, because remember that if we're going to let that be u, we'll just write it as u squared inside the integral. If you prefer to look at this as cotangent 1/2 x for the derivative, I prefer to see it that way, so you might want to write it like that. Now, when you take this derivative, you're going to have to use the chain rule. So the derivative of cotangent, we already said, was negative cosecant squared. So we'll write this as negative cosecant squared 1/2 x, and don't forget to chain on the derivative of the inside function, which in our case is 1/2 dx. So if you don't know your derivatives, you're not going to be able to integrate. Also, friendly reminder that you cannot multiply the 1/2 x and the 1/2 together. It does not work that way. When you rewrite this, du is going to be negative 1/2 cosecant squared. And now if you want to switch it back to x over 2, just because you know you're going to be substituting, that's fine. You can switch it back. And now, since you don't have a negative 1/2, as a constant multiple, you can multiply both sides by negative 2. And you'll get cosecant squared x over 2 dx. So it's one of these ones where you would think it would be obvious, but it's not. Also, just so you know, most of the time when you end up with a negative du, and you're going to end up having a negative in front of your integral, when you switch your limits, you're going to end up having them switch such that the order goes from greatest to least. So we might have to do another switcheroo here, which you know I like. All right, so this is your negative 2 du. And then your cotangent squared x over 2 will just be u squared. But now we also have to switch your limits. And if this is annoying you because you already feel like, ugh, I have to use x equals pi over 2 and pi over 3, and I'm going to have to do trig, you're going to have to do it anyway. Whether you back substitute and do it or do it here, you're going to be doing the same thing. All right, u was the cotangent of x over 2. You have to know your trig values. So this will be the cotangent of pi over 2 over 2, which is the cotangent of pi over 4. Well, the tangent of pi over 4 is 1, and the cotangent is 1 over the tangent. So this one's not so bad. That one's just 1. Remember, you can always enter this in your calculator as 1 over the tangent of pi over 4 if you feel more comfortable with that. And in this case, it would be exact, so you don't have to guess what the angle is. All right, a little bit harder for pi over 3. U equals the cotangent of pi over 3 over 2. So the cotangent of x over 2 is the cotangent of pi over 3 over 2, which is the cotangent of pi over 6. You might find this to be easier writing this as cosine pi over 6, cosine pi over 6 divided by sine pi over 6. That assumes that you are comfortable with these special trig angles, which you should be. The cosine of pi over 6 is root 3 over 2. The sine of pi over 6 is a half. That means that your value here is root 3 over 1, which is the square root of 3. Okay, questions so far? I feel like I've been talking for a while. I don't know what else I'm going to do, but okay. Okay, so let's rewrite this integral as, remember we're using negative 2 du, so we'll go negative 2 times the integral from the square root of 3 to 1 of u squared du. And you look at this and you're just like, what the heck? How did I have something so crazy and it turned into this, which it's really not that crazy. That's the beauty of integration by substitution. All right, if you're familiar with the square root of 3, it is more than 1. It's like 1.7 something. If you would like, and I would like, because this is going to drive me crazy, I'm going to rewrite my integral so that I have a positive 2, and I switch the order of my limits to go from least to greatest. And that's, again, using that property that we used back in example 16 at the beginning of class. And you don't have to do that. I just think it'll make your life easier to not have to deal with that negative in the front. Just my 2 cents. All right, so you're looking at 1/3 u cubed, and you're taking that from 1 to the square root of 3. Do not back substitute because you have your limits now written in terms of u. I didn't actually formalize that, but we showed it up here. And now we have 2/3 times the square root of 3 cubed minus 1 cubed. Now, if you're writing the square root of 3 cubed, you can write it squared and then multiply it by another factor of the square root of 3. Because when you are multiplying with the same base, you add the powers. So you can split it up as 2 and 1. The reason I would suggest that is because then when you square the square root, you can take the radicand out. Again, not something you have to do. Just something that I think looks cleaner. Now, of course, there's nothing here stopping you from writing this as 2/3 times 3 to the 3/2 minus 1. Also equivalent. I just feel like this is much more straightforward, and it would be where I would go as a student versus here. And if you're not sure how to get this, it's because you remember when you rewrite a radical using a rational exponent, the numerator of your exponent is the 3, and the denominator is the index of your radical, and the index for a square root is always 2. So this would be 3 to the 3/2 power. So maybe you would have gone from here to there. And both of them are fine. It's just a matter of personal preference. Okay, so now I want to go through some inverse trig examples. Before I do that, does anybody have a question here? So I did 2 inverse trig functions on the asynchronous work. I think I have 2 of them for you here now. Okay, so we're going from 0 to 1/6, and you have 3 divided by the square root of 1 minus 9x squared dx. Now, you saw some of these on your homework that you did over the weekend. You saw some inverse trig integrals in 5.5. I did not get a single question on them. So, I mean, there could be a number of reasons for that, but hopefully those went okay. We're going to do them now, just taking this extra step here to apply the definite integral to them. Now, the ones that I did asynchronously had a value other than 1 here, and we said we had to make it a 1. This one is already a 1. Now, this is good. This is an ideal situation. I want to make sure that we understand that this is not a u substitution, not directly anyway, not your basic u substitution, because we'd be taking u as 1 minus 9x squared, and then you'd get du is negative 18x dx. Well, there's no x in your numerator. So that would be the problem. You'd have negative 1/18 du is x dx. Well, we have no x. So that's how you know that this is not a standard u substitution problem. We can't just create it out of thin air. We don't have it. sometimes students are trying to find crazy workarounds for this, where they'll be like, well, what if we solve for x here and then take a square root? And then you get this nasty mess where you're doing plus or minus the square root of something in terms of u. And I don't know. Feel free to work around with that if you feel like it would be helpful. But since it's an inverse trig function, I doubt it would be. I mean, how are you going to get an inverse trig function to pop out of there? Okay. That's just my 2 cents. Okay, so the nice thing, like I said, is this already is written in the form of an inverse sine function. The inverse sine of u, we know that because it's the square root of 1 minus u squared. We just need to write this as u squared being some quantity that's squared. Right now, we don't have a quantity being squared. The value that's being squared is the x. The 9 was already squared. I'm going to pull the 3 outside, by the way, just because it distracts me if I don't. I'll move the dx into the numerator. You don't have to. I just feel like I want to put it there. So we're going to rewrite this as a quantity that's being squared. And in order to get 9, you'll write that as 3 squared. So to get 9x squared, take the square root of 9 and you get 3. 3x times 3x is 9x squared. Okay, so now this is in the form du over 1 minus u squared. Well, the du part we're going to have to fix. But remember that we are looking for, or what we want, is the integral of du divided by the square root of 1 minus u squared. That's what we're going for. So the 1 we already had in this instance, now we have the quantity u squared. Well, now I can rewrite this so that we can say that u is 3x. So yes, technically it's still a u substitution. It's just not your standard composite function. I should say that. The derivative of u is 3 dx. 1/3 du is dx. Okay, so we have a couple more things to do here, but let's sub in what we have so far. We have a 3. We're going from x equals 0 to x equals 1/6. The dx is going to become 1/3 du. And in the denominator, we have the square root of 1 minus u squared. Now, for the most part, the hard part is over for this one. Does anyone have questions here? All right. Yes. See if I can find a happy medium. Oh, that'll work. Okay, so now we have to switch to u limits, so we'll do that. Okay. If I'm going to switch to u limits, I know that u is 1 minus 9x squared. I have x going from 0 to 1/6. U is 1 minus 9 times, in this case, 1/6. So, oh my gosh, I'm using the wrong u that I said not to use. Let's see, sorry. I just was looking at my u here. I should have x'd that out as like a do not do. U is 3x. 3 times 1/6 is 1/2. 3 times 0 is 0. I'm going to even box this off just because there's a lot going on here. All right, so now I can rewrite this. By the way, the 3 and the 1/3 are going to cancel. So I'm just going to have the integral from 0 to 1/2 of du divided by the square root of 1 minus u squared. And now this is exactly where I want it to be, because I know that if I take the derivative of the inverse sine of u, I get du over 1 minus u squared under the radical. So I can integrate this and say that we have the inverse sine of u, and we're going from 0 to 1/2, and I don't have to back substitute because I already have these limits written in terms of u. U equals 0, u equals 1/2. You just need to know your sine values now, or technically your inverse sine values. So we'll have inverse sine 1/2 minus the inverse sine of 0. Remember that an inverse trig function is asking you for an angle. It's telling you what the value of the trig function is, and you're trying to figure out what the angle is that has that corresponding trig function value. So I feel like 0 is usually one of the easier ones to find. You know that the sine of 0 is 0, so the inverse sine of 0 is also 0. Also, you can find that in your calculator. If you plug in inverse sine 0, it's going to give you 0. So that one, no big deal, is 0. This one, you'll just have to figure out what the angle is. The inverse sine of 1/2 is pi over 6. We used that in that cotangent problem we did, I think, in the last example. This is because the sine of pi over 6 equals 1/2. Remember, with inverse trig functions, you're not looking for like 2 different places where that occurs. The inverse trig function for sine, if it's positive, is always defined to be in quadrant 1. So your solution here is, or your value for the integral is pi over 6. Questions on number 20. We'll do one more inverse trig function. Example 21. This is the integral from the square root of 3 to 3 of 6 divided by 9 plus x squared dx. Okay, now again, if you wanted to try a u substitution here, you'd probably try to let the denominator be u, but then you'd get du equals 2x dx, and you don't have an x up here. So that wouldn't work for you. And then you'd look at this again and be like, wait a second, this looks like du over 1 plus u squared. I just need to make it fit the form. And that's exactly what we're going to do. I did one very similar to this on the asynchronous work in 5.5. We're going to take your constant in the denominator and we're going to make it a 1, because what we want is some sort of integral that looks like this. The integral of du over 1 plus u squared, which we know is equal to the inverse tangent of u. So that's what we're going for. Now, I do this differently every semester apparently, but when I did it in the asynchronous work, I showed this using division. So I'm going to stick with that. If you would like to leave the limits on for now, that's fine. I'm going to divide each term by 9. So that I can make this constant in the denominator a 1. But when I divide one term by 9, I have to divide all the terms by 9. So now I can rewrite this. If you want to move the 6/9 in front as 2/3 by reducing the fraction, fine. Then you'll have a dx in the numerator, and then a 1 plus. Now you're going to have to write x squared over 9 as a quantity being squared. So that will be x over 3 quantity squared. If you take x divided by 3 and multiply it by itself, you'll get x squared over 9. All right, now I just did a lot of things here. Does anyone have a question before I continue? Okay. So the two important things we just did were that we made the constant term in the denominator a 1, and the variable term in the denominator we made as a quantity that was being squared. Now, once we have that, we can write u as x over 3, or if you are like me and you prefer 1/3 x, write it as 1/3 x. Same thing. Du is 1/3 dx. Now, you don't have a 1/3 dx. Technically, you have a 2/3 dx. It's up to you how much you want to work with that. Personally, I would rather just substitute out my dx and then deal with this guy later. Up to you. But if you want, you could multiply both sides by 2 and create the 2/3 dx. I just haven't been doing that so far, and I don't want to really confuse anybody. So I'm going to stick with doing what we have been doing. So we'll say that 3 du equals dx. Okay, so let's start to rewrite this, and then we'll switch out our limits of integration. So right now, since I'm going to write everything in terms of u, I want to make sure that I write x equals on my limits of integration, just so that I make sure it's really clear that they're not in terms of u. So dx is 3 du, and then I'm dividing by 1 plus u squared. Okay, so now we're going to switch to u limits. I have u equals 1/3 x. X was going from the square root of 3 to 3. So u is going to be 1/3 times x. Your new upper limit is going to be 1. And your new lower limit is going to be the square root of 3 over 3, which is a special trig function value. If you don't remember it, you'll have to look it up. It definitely corresponds to tangent, so we're in the right direction here since we're going to end up with an inverse tangent integral. Okay. So now we'll rewrite this again. When I do that, I'm going to cancel out the 3's, and I'm just going to have a 2 in front of the integral, And now my new limits are u equals root 3 over 3 to 1, and my integral is du over 1 plus u squared. Questions here? Okay. Well, we already said that the integral of du over 1 plus u squared is the inverse tangent of u. So go ahead and integrate. Don't forget that there's a 2 in front of your integral. So this is 2 inverse tangent u, and you're going from root 3 over 3 to 1. So I'm going to take twice the inverse tangent of 1 minus the inverse tangent of the square root of 3 over 3. So you're asking yourself, what angle has a tangent of 1? And hopefully we're really familiar with that one as being pi over 4. The other one, you're asking yourself, which angle has a tangent of root 3 over 3? It just happens to be pi over 6. You can always check that using your unit circle by using your quotient identities for sine and cosine if you don't know your tangent identities. I'm pretty sure I wrote these all down for you at some point. If not, you can feel free to have a chart with your trig, special trig values on it. And then pi over 4 minus pi over 6 is, let's see, get a common denominator. 3 pi over 12 minus 2 pi over 12 gets you 2 pi over 6. And of course, these should be left exact. So if you didn't know the inverse tangent of the square root of 3 over 3, and you just put it in your calculator and give me an approximation, that's not okay. You didn't take trig just so that you could approximate an inverse tangent for a special angle. There's a reason trig is a prereq for calc. You're supposed to know it before you get to calc. I have to get off that topic very quickly. I want to show you an inverse trig function that does not look like an inverse trig function. It's in disguise. But it pops up more often than you might imagine, which is why I'm going to show it to you. Example 22. This is the integral from 0 to the natural log of 5 of e to the x over 1 plus e to the 2x dx. Now, this is actually in the form of an inverse tangent. It's not obvious by looking at it, but it actually is in that form. And if you weren't sure, what you would try to do first is you would try letting the denominator be u. And then you would get du equals 2 e to the 2x dx. And then you'd end up with an issue here because you don't have e to the 2x, you just have e to the x. So even if you said, all right, fine, 1/2 du is e to the 2x dx, Okay, now what? Remember that e to the 2x is just e to the x times e to the x. When you are multiplying with the same base, you add the exponents. You can't just divide out e to the x on both sides. That's not how substitutions work. Even if they did, that wouldn't fly in this particular situation. So you would be stuck. What you're supposed to do is recognize, I'm going to rewrite this, and I suggest you also rewrite it, that e to the 2x can also be written as e to the x squared. For the same reason that you saw this here, e to the x times e to the x is e to the x squared, but also when you take a power to a power, you multiply the powers. 2 times x is 2x. And if you're still kind of like, I don't know if I would have recognized that, that's partly why I'm going over this with you. I go over a lot of examples that, I mean, I can't go over every possible example you're going to see, but I try to cover situations where maybe a standard use substitution wouldn't work and you're not sure what else to do. Right now, you only have a limited number of tools in your belt. There are only so many things that you can do here. So if you can't do a regular integral on this using the power rule, and you can't use a substitution, maybe try to go for an inverse trig function. And notice that anytime you have 1 plus a quantity squared in the denominator, that should be triggering inverse trig to you. Now, if you're wondering, like, wait a second, doesn't she keep saying inverse trig functions have constants in the numerator? No, I'm saying that inverse trig functions always have du in the numerator. And normally, if we have 1 plus x squared in the denominator, du is dx. That's why normally you see a constant in the numerator. Not in this case. This is of the form inverse tangent u. You're going to let u be e to the x. Oh, and remember, I know we just did one of these, but we're on another page now, so we're going for du over 1 plus u squared. So if we let u be e to the x, then e to the x squared we have, which is what we're looking for here. The nice thing here is du is e to the x dx. You have that also. This will be your du. And then normally we would take this constant and make it a 1. It already is a 1. Already 1. Check. Perfect. That's great news for us. We can go ahead and start our substitution now. So let's go ahead and rewrite this in terms of u. We're going from x equals 0 to x equals ln 5. We have du divided by 1 plus u squared. Now, we don't even have to do anything weird to manipulate this integral. It's already basically ready to go. All we have to do is switch the upper and lower limits of integration and evaluate this using the FTC. Before I do that, are there any questions here? Fantastic. Switch the u limits. X equals ln 5, x equals 0. We said that u was e to the x. So we'll have e to the ln 5, which simplifies to 5. And u equals e to the 0, which is 1. So we're going to go from 1 to 5 of du over 1 plus u squared. And this is the inverse tangent of u from 1 to 5, which is the inverse tangent of 5 minus the inverse tangent of 1. Now, 1 is a special angle. The tangent of pi over 4 is 1. However, I don't know an angle whose tangent is 5. That's not a special trig function value. That's something that you're going to leave exact as the inverse tangent of 5. You are not going to give a decimal approximation. You're going to leave it as the inverse tangent of 5 minus pi over 4. If you can evaluate it, do it. Make it exact. Don't give me a decimal, no matter what. Even if neither one of them is a special trig angle, doesn't matter. Just leave it exact. Okay. Questions on 22? It's like integration heaven today, isn't it? Oh, so many things that we're getting to see in calculus. Right here in the last day, too. I always feel bad that the last day has to be so heavy. I can't help it. That's just the way the course is structured. I always wish we could do this like last week and then end on something nice and light, but this is the way it's structured. Okay, so I'm going to do one that's not necessarily hard, but it might be one that's a little bit harder to recognize. So we're going to go from 0 to the square root of 2 over 2. And this is the inverse cosine of x divided by the square root of 1 minus x squared dx. Okay, now, on first inspection, you might be thinking that this looks like an inverse sine problem. However, if you wanted this to be an inverse sine of u, you would have to have du up here. So if you wanted to try inverse sine u, then u would be equal to x in this case, because you're taking 1 minus u squared, so 1 minus x squared. And du is dx. Okay, but what are you going to do about this thing? You don't have that thing. So you don't actually have this form. So I'm trying to show you examples and things that you're going to look at, you're going to try, it's not going to work, you're going to try something else. And unfortunately, that's just the process of integration. Trying things, failing, trying something else. But if you remember something about a standard u substitution, you know that you're looking for a function and its derivative. Well, if f of x is the inverse cosine of x, then f prime is -1 divided by the square root of 1 minus x squared. So you actually have a standard u substitution here. If we let u be the inverse cosine of x, and I know we don't usually let u just be the numerator, but that's what's going to work for us in this case. It's just kind of recognizing what we have and what we have to work with derivative-wise. Du, remember for the inverse cosine, it's negative. It's -1 over the square root of 1 minus x squared dx. And now you're in a situation where you really just have -u du. We don't have a -1, so if you want to just make that -u, then do that. Okay, so let's swap it out. We have x equals 0 to x equals root 2 over 2. And then you have negative du for your, negative du, sorry, is 1 over 1 minus x squared under the radical dx. So this whole thing right here, I've got all these clouds going on, is negative du. So we have u du. Maybe I'll put that in parentheses. Okay, now remember when I said if you have a negative in front of your du, you're probably going to end up switching your limits and they're going to be reversed in order from greatest to least. So that's probably going to happen. But let's go ahead and switch our limits. We have u equals the inverse cosine of x. We have x going from 0 to root 2 over 2. So u is going to be the inverse cosine of root 2 over 2. So you're asking yourself what angle has a cosine value of root 2 over 2. Hopefully we remember that's pi over 4. Cosine and sine have the same value there. And then we're asking ourselves which angle has a cosine value of 0. Don't say 0, because the cosine of 0 is 1. The cosine of pi over 2 is 0. Now notice, like I said, instead of going from least to greatest, you're going from greatest to least. So I'm going to switch those when I put them in the integral. I'm going to rewrite it the way it is for now, and then I'm going to show the switch. So we'll have the negative integral from pi over 2 to pi over 4 of u du. And then we'll switch this out to be the positive integral from pi over 4 to pi over 2 of u du. It's in a little box. All right, so we integrate u as 1/2 u squared, and then we just take it from pi over 4 to pi over 2. So we have 1/2 times pi over 2 squared minus 1/2 times pi over 4 squared. Which is 1/2 times pi squared over 4 minus 1/2 times pi squared over 16. And you can simplify this. It's pi squared over 8 minus pi squared over 32. Let's see. 1/8. Here's my calculator. 1 over 8 minus 1 over 32. Is 3 over 32. Pi squared. So that's another non-standard example. Something that could pop up that's, getting planted in your brain so that if you see something like it again, you'll be thinking, wait a second, I think I saw her do something like this. Maybe not with the same functions, but same idea. You guys want to end with the longer problem, or do you want to end with the easier ones? Can't remember what my students said last semester, but it surprised me. Does anyone care? No one cares. All right. Then let's get the easier ones out of the way. We'll do the longer one at the end. It's not like a really hard one, it's just a little bit longer. Okay, so the next two examples are going to use this formula. So we're going to do integrals involving f of x equals b to the x, or technically it could be like b to the u. So it could be like f of u of x is like b to the u of x, something like that. Your formula for this is going to be the integral of b to the u du is b to the u. I don't ever remember this. That's why I'm referencing my sheet here. Divided by ln b plus c. If you want to highlight that so that you can easily find it for your test, I might throw one of these on here. It's not supposed to be super tricky. It should just be for easier points. I'm pretty sure I gave this to you when I gave you that big list from the table in the book in 4.8 when we talked about antiderivatives. I'm pretty sure this was on here in its form b to the x instead of b to the u, but obviously nothing is different about the form. It's just swapping out u for x. So this will be example 24. Three to the 2x dx. And you might have seen some of these on your homework because, like I said, we technically did go through these derivatives, and I did give you the formula in that table. I can't remember if I included any of them in the homework or not. So we're referencing this formula. B is just your base. That's not a variable. So this is not when you're taking a power of a function. This is when your base is some sort of constant value, not e, and your exponent has a variable in it. So we're going to let u be 2x because that is the exponent in our case. Then du is 2dx. 1/2 du is dx. And this is really pretty much just applying a formula. So it's not supposed to be super tricky, like I said. So the dx is going to be the 1/2 du. And then we just have over here 3 to the u. So the base just stays whatever the base is, which in this case is 3. So we're going to rewrite this. And I didn't even put limits of integration on this one. 1/2 3 to the u du. And then we'll use the formula. So now we're in the form b to the u du. We'll integrate this as 1/2 times 3 to the u divided by ln 3 plus c. We're doing a plus c now because we switched back to indefinite integrals. Don't forget your plus c. And then we'll switch out u for 2x. So we'll have 3 to the 2x divided by 2 ln 3 plus c. All right, so we'll do one more of these, and then I'll do the longer one, and then we'll be done. Example 25. we're going from 0 to 1. The integral is x times 5 to the negative x squared dx. Now we are in the form b to the u, or at least that's what we're going for. So you're going to let u be the exponent, which in our case is negative x squared. And then du is going to be negative 2x dx. You don't have negative 2x dx, you just have x dx. So go ahead and divide out negative 2 on both sides to get x dx. And then this guy will just be 5 to the u. Now don't forget to switch out your upper and lower limits of integration. If you'd like, we'll switch them now, since we know we're going to do it anyway. So I'm going from x equals 0 to x equals 1, and I know that u is negative x squared. Whatever you do, don't say that this is like negative 1 quantity squared. The 1 is the part that's being squared, and the negative stays out front. And because we have this negative du, you're seeing that the order of your limits for integration is reversed. So officially, we have negative 1/2 times the integral from 0 to negative 1, and these are our u limits. The negative 1/2 comes from the du, and then we have 5 to the u du. And because I like to have this in the order from least to greatest, and I don't like the negative in front, I'm going to say this is positive 1/2 times the integral from negative 1 to 0 of 5 to the u du. And then I'm just going to apply the formula. So the formula is b to the u over ln b. So this will be 5 to the u divided by ln 5, and we'll evaluate that from negative 1 to 0. And because I have the limits written in terms of u, I don't have to back substitute. So we'll have 1/2. If you want, you can just write this as 1 over 2 ln 5, since that's not going to change anyway. And then you have 5 to the 0 minus 5 to the negative 1. This one's going to be a slightly more work to simplify. 5 to the 0 is 1. 5 to the negative 1 is 1/5. And then that's all being divided by 2 ln 5. Well, I guess it's really not that much work to simplify, really. One minus 1/5 gives you 4/5. And then you can multiply by 5 in the numerator and denominator to simplify the complex fraction. So that will give you 4 times 10 ln 5. If you want, I skipped an intermediate step. I'll write it down. And then between the 4 and the 10, you can simplify as 2/5. And leave it exact. All right, I have one more questions on this one. Last one, you guys. Last example of Summer Calc 1. I told you this class would end before you know it. It would be over. It's just going to fly by. Did it fly by? Oh, like, I feel like in a way it did, but in a way it didn't. It still felt like 8 weeks, I guess. That's just my opinion. All right, here it is. Oh, I love this example. I love this. In the numerator, 3x plus 4. In the denominator, the square root of 3 minus x squared dx. Now, I'll tell you why I love this one. Because normally I would say, like, okay, here's what you're going to try, and it's not going to work. But in this case, what you are going for and the thing that you were going to try that wasn't going to work, both of those things are going to work. You have to apply both of them. So that being said, you might be looking at this and thinking, okay, I have the square root of a constant minus x squared. And you might be thinking, based off everything we did tonight, that this looks like it's in the form of an inverse sine. But then you'd have a problem, because if this was an inverse sine and you let u be x, so you could get u squared, then du would just be dx. Well, you have this x that's unaccounted for. And then if you were thinking standard u substitution, you would say, okay, fine, I'll let u be the radicand. This is what we would have done earlier in the lesson. We did some of this asynchronously. You would let u be the radicand. Now, this is actually going to work for us. So you'll want to write this down. I know normally I say try this, it doesn't work, and I cross it out, and then you feel like, why am I writing all this? It was a waste of time. We're actually going to use this information. All right, so u equals 3 minus x squared, standard u substitution. Try it, see what happens. The derivative of u is negative 2x dx. Okay. Now, the nice thing is you're looking at your numerator and you're noticing that you do kind of have an x dx. Kind of. Now, where some students go wrong is they try to create the numerator over again. So here's what they try to do. Okay, this is what we're going to use. What they say is, okay, well, clearly I have a 3x plus 4 dx. So they want to create a 3 dx. So they multiply on both sides by 3. Fine. And this is fine. You can technically use this. I'm good with this. What you can't do is this. You cannot do that. This is a big fat no. You can multiply and divide all you want to create the dx piece that you need, but you can't add to it. So what you can do is split this integral up into 2 separate integrals, and that's what you're going to have to do. What you're dealing with here is a situation where you have 3x divided by the square root of 3 minus x squared dx plus, and it's up to you if you want the 4 in the numerator. I'm just going to leave it there for now so it's very, very clear where everything came from. 4 divided by again, the square root of 3 minus x squared dx. So it's just that same concept of splitting up the fraction and keeping the denominator on each term. Same idea. You're going to have to use that in this particular situation because you actually have two different forms here. This one is your standard u substitution. This one is that arc sign. You have to do these two separately. And the nice thing is we have these properties of integrals that state that once we find each integral, we can just add them together. So that's what I'm going to do. I'm going to focus on the u substitution first because we already did so much work for it. Why not use it? And then we'll do the inverse trig function next. Okay, so we'll do this one first. Oh, by the way, if you want my plan, evaluate each integral separately. Then sum them. And this is a really important skill, by the way, that you're going to need in Calc 2. Just being able to recognize when do you have an inverse trig integral, when do you have a u substitution. And the big thing, the big difference lies in whether or not you have an x. So this one's got an x in the numerator, it's a u substitution. This one does not, it's an inverse sign. So we did all the work here using u equals 3 minus x squared. We even created the 3x dx by taking negative 3/2 du. So I'm going to rewrite this integral over here just so that we can solely focus on it. This is the one that we're doing first, and we're now going to write it in terms of u. We had 3x dx as negative 3/2 du. I'm going to put the negative 3/2 in the front. I'm going to put the du in the numerator. And then in the denominator, we have the square root of u. And this all goes along with this u substitution that we created up here. Now, of course, if we're going to integrate this, we're going to want to rewrite it as u to the negative 1/2 du. So we have negative 3/2. We're going to increase the exponent up to positive 1/2. Instead of dividing by 1/2, we'll multiply by 2. And then we'll back substitute for x. If you want to write your plus c, you can. I know sometimes we do it automatically. You can just wait and do it at the end if you want. Does not matter. As long as it's in your final answer, I don't care if you include it in the intermediate steps. So the 2's will cancel, and you'll be left with negative 3, and then the square root of u is the square root of 3 minus x squared. Okay, so this is equal to our first integral. I'm just rewriting it here so it's very clear when we look for it later. That thing. But now we're going to integrate 4 divided by the square root of 3 minus x squared. Before I do that, are there questions here? And it doesn't matter what order you do this in. I just already started with the u sub, so I went with that one first. And if you want to leave the 4 in the numerator, fine. We'll fix it later. Now, we did a bunch like this last time. We want to make this a 1. It is not currently a 1. So we're going to have to do a little bit of work here. The way I showed this last time was with division. So to make it a 1, you'll divide by 3. What you do in the denominator, you must also do in the numerator. However, this is tricky with the radical. You didn't just divide by 3, you divided by 3 under a radical. What you do in the denominator, you must also do in the numerator. If you divided by 3 under a radical, then you need to divide by 3 under a radical in the numerator. Don't forget your dx. Okay, now we're going to simplify. Kind of depends on what you want to do. I'm going to leave this here for now. Well, no, I don't like to leave a fraction in the numerator. I'm going to pull it out. We're going to end up manipulating it somehow anyway. So this will be the square root of 1 minus. Now be careful here because you want the quantity squared. 3 is not being squared right now. In order to write it as a square, you're going to have to write it as the square root of 3 because the square root of 3 squared gives you 3. Your goal here is to make these two exactly the same as they were, just in a different form. So x over root 3 times x over root 3 is x squared over 3. You haven't actually changed anything. All right, but we're in a good position now because we have this already a 1. Awesome. Now we're going to set up a new u substitution. If you want it to be a w, that's fine. If you want it to be a u, fine. I'm going to write it as a w just because I already have a u substitution up there and I don't want to have 2 different u's going on. So this is 1 over the square root of 3x. Some students just don't like w and they want it to be u all the time. So if you don't like w, just make it a u. dw is 1 over the square root of 3 dx. Okay, now this is one of those places where you might say, well, I don't have 1 over the square root of 3. I have 4 over the square root of 3, and you could multiply on both sides by 4. Or you could just cancel it out in a minute. It's one more step, but you might find it to be more straightforward. And instead of doing this in terms of u, we'll rewrite it in terms of w. Okay, so the dx is going to become root 3 dw. So I have 4 over root 3 times the integral of the square root of 3 dw divided by the square root of 1 minus w squared. And now this is where you would cancel out those square root of 3's. So like I said, it's one more step, but if you find that to be more straightforward, then just do that. So now you have 4 times the integral of dw over the square root of 1 minus w squared, which is where your inverse sign of w comes in. And if you want to put a plus c on it, fine. Like I said, whether you do that now or later makes no difference to me. Back substitute for x. We had w as 1 over the square root of 3. You don't have to rationalize that. You can just leave it. So this is 4 times the inverse sine of 1 over the square root of 3 plus c. And if you're wondering, like, oh my gosh, is this some crazy, oh, I forgot my x. Is this some crazy inverse trig value that I should know, but I don't? It doesn't even matter because we don't have a definite integral, so you don't need to worry about it in this case. But now we know that this is equal to that integral. So you can go ahead now and add the 2 together. So we can say that the integral of 3x plus 4 divided by the square root of 3 minus x squared dx is equal to negative 3 times the square root of 3 minus x squared plus 4 times the inverse sine of x over the square root of 3 plus c. I love that problem. Oh, I just love it. I don't know why. I guess just because I feel like it just kind of takes everything that we learned and combines it into one problem, which is always a good thing. All right, I'm 2 minutes over again. Yowza. I'm going to put up some homework for you guys to practice what we learned this evening. And it'll be your last homework assignment. It will be due on Thursday. Normally, oh yeah, I guess, oh, you know what? It's normally due Wednesday, right? I mean, it doesn't really make sense to have it due Thursday because your test is Wednesday. So let's have it due Wednesday. So the 5-5 part 2 will be due Wednesday, and your test 5 is Wednesday, and your final is Thursday. Like I said, tomorrow, oh, sorry, writing and it's too low. Tomorrow I'll be on at 6. If you are on till 8:10, that's fine. If you are not, fine. If you don't come on till 7:30 and I have no one sitting here, I'll still be up here until 8:10, ready to answer your questions. So let me know if you have questions. The key for the final exam review is online. I will see you on Wednesday for test 5 and Thursday for the final exam. You have no more quizzes, so don't ask me if you have a quiz Thursday because that wouldn't make any sense. I don't think anyone would have asked, I guess. But that's all. It's been a pleasure, you guys. Hopefully I'll see some of you tomorrow. If not, then I'll see you on Wednesday. Have a wonderful evening.
You too. Thank you.
Thank you.